Welcome, you curious mind. You're looking to understand the deep stuff, the really fundamental ideas, without getting bogged down in, a swamp of equations.
hmm
Consider this your shortcut. Today, we're diving straight into the fascinating and often counterintuitive world of cutting-edge physics. Loop quantum gravity, or LQG,
Right.
and our expert guide. Well, it's the insights of Carlo Rovelli from his article, Loop Quantum Gravity, Carlo Rovelli Theories of Everything.
Yep.
Think of this as unlocking the secrets of reality's very foundation, based on what Rovelli himself has laid out.
Precisely. And what's truly illuminating about Ravelli's perspective and, what we're aiming to clarify for you is how it challenges some of our most deeply ingrained yet frequently misunderstood assumptions about the quantum universe and the nature of space-time itself.
Right.
Our goal is to extract those key insights, those moments where things kind of click into place, leaving you with a richer, more accurate understanding.
Okay, let's unpack something right away. We often picture the quantum vacuum as this incredibly busy, almost boiling space, right? Constantly generating virtual particles. It's an image of nonstop activity.
Yeah, that's the common picture.
But Rovelli presents a surprisingly different view, doesn't he?
He does. A major insight from Rovelli is that our intuitive picture of the quantum vacuum as constantly bubbling with energy is actually, well, incorrect at its fundamental level. It's surprisingly stationary.
Stationary.
Yes. While virtual particles do exist, the underlying state of the vacuum itself doesn't change over time.
A stationary state. Even with the presence of these virtual particles, that really goes against the grain of what many of us imagine.
It does.
Can you maybe paint a picture to help us grasp this?
Okay, think of a calm ocean. On the surface, you might see ripples and small waves. Those represent the quantum fluctuations of a virtual particle. But the ocean itself, deep down, is still. Or picture a perfectly still lake. The potential for waves is there, but it's currently undisturbed. The virtual particles represent a potentiality, not necessarily a constant physical churning of the vacuum itself.
Right, so it's more about potential energy waiting to be released, rather than like a continuous display of kinetic energy at the fundamental level.
Exactly.
Now, let's shift our focus to particles.
Yeah.
We tend to think of them as tiny marbles with a precise location, but quantum mechanics throws a real wrench in that classical picture, doesn't it?
Absolutely. And building on this idea of a fundamentally probabilistic quantum vacuum, let's now consider how this probabilistic nature extends to the very particles within it. The classical idea of a particle having a definite position. It simply doesn't hold in the quantum realm.
Just no tiny marbles zipping around.
Nope. Before we measure it, a particle's location isn't fixed. It exists as a probability cloud, often described mathematically as a Gaussian wave function. Think of it as a blurry cloud where the densest parts indicate the most likely locations.
A probability cloud. So it's not that the particle is darting around randomly. It's more that it has a higher chance of being in certain places than others.
Precisely. And this is where the notion of a particle jumping comes in, which Rovelli clarifies is a misunderstanding.
Ah, okay.
When we perform a measurement, we're essentially forcing the particle to manifest at a particular point. But it wasn't jumping there. Our measurement simply lands within that pre-existing stable probability distribution.
He uses a really effective analogy to illustrate this, the blindfolded archers and the foggy target. Can you walk us through that picture?
Certainly. Imagine archers firing arrows at a target that's completely obscured by fog.
Right.
The fog itself isn't moving. It's a stable, albeit hazy, entity. Each arrow, representing a measurement of the particle's location, will strike the wall in a different spot.
Okay.
But that doesn't mean the target itself, the underlying probability distribution of the particle's location, is jumping around. Our measurements are simply sampling that stable distribution, giving us different results each time. That's the essence of quantum spread.
Okay, that foggy target really helps make that abstract idea more concrete.
I like that. Now, the term quantum often brings to mind the idea of things being made of discrete units, like pixels forming an image. So when we encounter quantum space-time, the initial thought might be that space itself is constructed from tiny, indivisible building blocks. But Rovelli challenges that intuition as well, doesn't he?
He does, and this is a crucial distinction to grasp. The idea that quantum space-time is discrete in the same way a digital image is pixelated is a common misconception.
Yeah.
Rovelli emphasizes that saying quantum spacetime is discrete can be just as misleading as saying a quantum particle is just a regular particle that moves erratically. It's not quite right.
So if it's not like miniature Lego bricks of space, then how does Rovelli describe this quantum spacetime? What's the alternative picture he paints?
Well, what's fascinating here is that Rovelli explains quantum spacetime as being described by what's called an operator value distribution.
Okay, operator value distribution. Essentially, each possible configuration of spacetime has a certain probability amplitude associated with it. Think of it like the volume knob for each potential configuration. A higher amplitude means that particular geometry is more likely to manifest.
So it's not a fixed structure.
No, not a fixed, discrete structure, but rather a probabilistic landscape of potential geometries.
Operator value distribution. That still sounds quite technical. Yeah. If we break that down further, especially when we consider quantum fields, I recall Rovelli drawing an important distinction there too.
Absolutely. In classical physics, we might think of a field like, say, the temperature in a room as having a specific definite value at every single point in space.
Right, a number everywhere.
But in quantum field theory, it's a more abstract concept. A quantum field isn't simply a value at each point kind of thing. Instead, as Rovelli explains, it's an operator value distribution. So instead of fixed values, we have possibilities waiting to be played through interaction.
An operator value distribution. So at every point in space, there's an operator, not just a number representing a value. What exactly does that imply about how these fields behave?
It means that these operators at each point only yield actual measurable field values when there's an interaction or a measurement takes place. Until then, they exist as these operators, these potential actions that can produce a value.
He used a really memorable analogy for this, something involving a jukebox.
Yes, the jukebox analogy. Think of a jukebox. Each slot in the jukebox holds a record, representing an operator the potential to play a specific song.
Okay, got it.
But the music itself, the actual field value, only plays when you insert a coin, which represents the interaction or measurement.
The interaction is the coin.
Exactly. Before that interaction, the potential for music is there in each slot, but no specific song is playing. Similarly, in a quantum field, the operators are present at every point, holding the potential for a specific field value, but that value only becomes concrete upon interaction.
So the universe is like a giant silent jukebox waiting for us to drop a coin in.
That's a fun way to think about it, yeah.
That jukebox analogy really makes that concept understandable. Okay, so if we apply this idea of quantum fields and operator-valued distributions to gravity, which Einstein described as the curvature of space-time caused by mass and energy, what does loop quantum gravity tell us about it?
Right, building on that understanding of gravity from classical relativity, where it's the curvature of space-time shaped by mass and energy, LQG offers a profound shift in perspective. In loop quantum gravity, gravity is still fundamentally about geometry, but it's a quantum geometry.
Quantum geometry.
Meaning what?
In practical terms.
It means that space-time itself isn't just some fixed background that gets bent and warped by matter. Instead, space-time exists in a superposition of different possible geometries.
Wow.
It's not just flat or curved in a singular, definite way. It's a quantum mixture of all these potential configurations happening simultaneously.
A superposition of geometries, similar to those layered, transparent geometric shapes he described.
Exactly. Imagine you have multiple transparent geometric shapes, each slightly different, some with a bit more curve here, a bit less there, and they're all occupying the same space at the same time, layered on top of each other.
Okay, I can picture that.
That's a conceptual way to visualize space-time in LQG, a superposition of these different geometric configurations until we interact with it or measure it in some way.
So we've moved from understanding the surprising stillness of the quantum vacuum to this mind-bending idea of space-time itself being a superposition. Rovelli's really painting a picture of reality that's far removed from our everyday intuition.
Completely. It's a radical shift.
That's a truly mind-bending image. Now, LQG also proposes the existence of a smallest possible unit of length, right? The Planck scale.
Yes, that's correct.
How does that idea fit into this picture of a non-classically discrete spacetime?
Well, this is another nuanced point. LQG does predict the existence of a smallest possible unit of length, the Planck scale. This does imply a certain fundamental granularity to spacetime, a limit to how finely we can probe its structure.
But not pixels.
But, and it's crucial to understand this, it isn't like space-time being made of tiny fundamental building blocks in the way we might imagine atoms forming matter.
Okay.
Instead, it's more like a fundamental limit on the resolution of space-time, a point beyond which our classical notions of space and length cease to be meaningful. So a granularity in the sense of a limit to divisibility rather than discrete building blocks. That distinction is important.
Right. A limit, not a block. Got it.
Yeah.
Now, Rovelli also laid out this really insightful evolution of our understanding of gravity, almost like progressing through different levels of understanding. Can you walk us through that layered perspective?
Yeah, Rovelli offers a beautifully layered explanation of how our understanding of gravity has progressed. At the first level, the, let's say, high school level, we have Newton's view. Gravity is a force acting between objects.
The apple falling from the tree.
Exactly. And as Rovelli points out, this is an approximate truth, perfectly adequate for many everyday situations.
Then we advance to the next level, Einstein's theory of general relativity, the university level.
Precisely. Here, gravity is no longer seen as a force pulling objects together, but as the curvature of space-time caused by the presence of mass and energy. This is a much more accurate and comprehensive description of gravity.
Explaining things Newton couldn't.
Right, explaining phenomena that Newtonian gravity couldn't, such as the bending of light around massive objects.
And then the current frontier, loop quantum gravity. What's the next level of understanding that LQG offers?
In LQG, we take another step, viewing gravity as quantum curvature, this superposition of possible geometries we've been discussing.
The layers again?
Exactly. This aims to reconcile gravity with quantum mechanics, describing the very fabric of space-time at the quantum level.
He also touched on concepts like torsion and non-metricity, mentioning that they aren't inherently necessary in the current formulations of LQG. What do these ideas represent, and why is it significant that they aren't strictly required?
Right. Torsion and non-metricity are more advanced concepts in the geometry of spacetime. Torsion relates to how spacetime might twist, and non-metricity relates to how lengths and angles might change as you move through spacetime in ways not solely attributable to curvature.
Okay, complex stuff.
Yeah. The fact that current formulations of LQG can describe gravity as quantum curvature without inherently needing these more complex geometric features suggests a certain elegance and potentially a more fundamental description. However, as Rovelli notes, it doesn't necessarily rule them out for future developments in LQG. They might still play a role.
It's fascinating how each new understanding builds upon and refines the previous one, rather than completely invalidating it.
Exactly.
It's like each level gives you a more nuanced and powerful grasp of the underlying principles. Now, shifting gears again, LQG is a theory about the fundamental nature of reality. And much like quantum mechanics itself, it grapples with its own interpretational challenges, correct?
Absolutely. That's a really important point. Just as there are various ways to interpret the implications of quantum mechanics, many worlds, pilot wave theory, and others, loop quantum gravity also encounters these foundational questions.
The what does it all mean question.
Pretty much, yeah. These interpretations attempt to make sense of the mathematical framework and connect it to our understanding of the physical world.
And Rovelli has a particular inclination towards one of these interpretations, doesn't he? The relational interpretation.
Yes. Rovelli has been a strong advocate for the relational interpretation of quantum mechanics, and he sees its principles as being applicable to loop quantum gravity as well.
So what's the core idea there?
Well, this interpretation emphasizes that physical properties of a system don't possess absolute intrinsic values, but rather exist and are defined relative to other systems or observers.
Okay, relative.
Properties emerge from relationships.
He's even giving lectures on this at Princeton, which really highlights the philosophical depth intertwined with these scientific ideas.
It does.
It's not solely about the equations, it's about how we fundamentally perceive reality and our place within it.
Precisely. The relational interpretation suggests that the properties we observe are not inherent to an object in isolation, but emerge from the relationships and interactions it has with other parts of the universe, including the observer making the measurement.
That's profound.
It is, and this perspective has profound implications for how we conceptualize space-time and quantum phenomena within the framework of LQG.
So as we begin to wrap up our exploration of Rovelli's perspective, he leaves us with this really thought-provoking idea. All our current theories, even something as sophisticated as loop quantum gravity, are essentially layers of approximation. We haven't reached the final destination with the definitive theory of everything.
That's a crucial takeaway. Rovelli emphasizes that our current understanding, as advanced as it is likely just one step in a long and ongoing journey of discovery. Each theory we develop, from Newton to Einstein to the ongoing work in quantum gravity, provides a more refined and accurate picture of reality, but none of them are likely the ultimate, complete answer.
And he concludes with that wonderful quote: "If the world was simple enough to be understood, we wouldn't be smart enough to understand it."
Yeah, I love that quote.
It's a humbling reminder of the universe's complexity and, I guess, the inherent limitations of our intellect, while also celebrating the remarkable progress we've achieved.
It truly is. It underscores the continuous nature of scientific inquiry and the fact that the more we learn, the more we become aware of the vastness of what remains unknown. The quest for a complete understanding of the universe is an ongoing process, fueled by our curiosity and shaped by our inherent limitations.
So, for you, our listener, what are the key insights to carry away from this deep dive into Rovelli's perspective on loop quantum gravity?
Well, the quantum vacuum isn't the chaotic free-for-all you might have imagined. Particles are more akin to blurry clouds of probability than fixed points in space.
Right.
And the very fabric of spacetime might be a quantum superposition of different geometric possibilities, not just a static stage upon which events unfold. And perhaps most importantly, our understanding of gravity is a continuously evolving narrative.
Exactly. This exploration into LQG, guided by Carlo Rovelli's illuminating insights, offers a glimpse into the truly bizarre and beautiful nature of reality at its most fundamental level. It serves as a powerful reminder that our intuitive, classical understanding of the world breaks down at these incredibly small scales,
Totally breaks down.
and that new, more abstract concepts are necessary to truly grasp the underlying structure of the cosmos. And on that thought, consider this. If reality itself is fundamentally built on probabilities and relationships, how might that subtly shift your understanding of your own everyday experiences and the vast universe around you? Even if that ultimate theory of everything remains just beyond our reach, the ongoing journey of seeking to understand is an incredibly rewarding endeavor in itself. Thanks for joining us on this deep dive.